Okay, so let's start. Can you hear me up there? Last row. Some of you cannot hear me still. Excuse me? Last row over there. Can you hear me? You're too busy. You look too busy to actually listen to me over there. Yeah, okay, good. Thanks. Okay, so where are we? So let's just start where we pretty much left off before we move to some administration and new things. So that's basically what we covered last time. You should know almost everything about decision trees. So this is the example we played with. It really bothers me that in the last row over there, you guys are doing other things. You don't have to come, but if you do, pretend that you're listening rather than doing other things. Thanks. And then once we know how to induce decision trees, we suggested this as an example. What was the problem? What is the problem that you can see in this example? Does not fit into the tree. If you take this example, you start with Outlook. This is how we evaluate the decision tree. Sunny, you go to your left. Then you check humidity, normal, and you think that you're done. But really, you would have said yes, but the label is no. So if this was the 15th example in your training set, you would have to modify the tree. This one doesn't want to work, okay. And you will do something like this. Second. So the problem with this isn't that it's not consistent with the tree. The problem is that you can always do this. And therefore, something is wrong, right? So you don't always want to modify the tree as a way to just agree with the training data. What's going to happen in the future when you really get examples with no labels and you want to be able to predict. So this is how we introduce the problem of overfitting. And basically the issue that I wanted to bring to your attention is that the training data is always going to be a tiny sample of the old data that you could see. And nevertheless, what you do is you learn a predictor on your training data. So you want to make sure that when you look at your training data, you have to take some precautions for how not to overfit the data. So we define overfitting, and we define overfitting by looking at these two curves. As a function of the complexity of the tree, we want to look at the accuracy of the hypothesis. And we're going to get to it later today. We define some measure of accuracy. So intuitively, we agree that as a function of the complexity of the tree, the accuracy on the training data is going to go all the way until you completely fit the data. At least when we deal with decision trees that we agreed is a very expressive class of functions. But on the test data, this is not going to happen. At some point, you're going to start reducing the accuracy. And at this point, we're going to start saying that we overfit the data. Okay, so that's where we left off last time, pretty much. I'm going to skip a few things that we talked about. And I want to go back to the discussion that we started to have on how to explain this phenomenon on overfitting. I started by asking you, why is this a shape that makes sense for the curves. And I just went over it again. Any questions on this? Everyone agrees that this makes sense. So we are typically talking about two things. One is the empirical error. And here, I tried to wake you up. This was at the end of the lecture. And you agreed with me, I hope, that this actually does not make sense. The empirical error should go down as a function of the complexity. As long as we're talking about consistent data, and we're talking about an expressive class of functions. And this is as a function of the model complexity. Now, we haven't defined model complexity. In decision tree, it's very easy to talk about model complexity. It's basically the number of nodes. In general, it could be the number of parameters, even though we gave an example last time when we talked about linear functions. And there, the notion of complexity was a little bit more involved. It really isn't the number of parameters, because the same looking linear function could be viewed as an expressive, as taken from an expressive class of functions or a less expressive class of functions. So this issue is something that we'll have to discuss in a little bit more details. But for now, given that we're talking about decision trees, it's a good enough thing to keep in mind. What we care about is not the empirical error, but rather the expected error. So let's think about it as what percentage of the items drawn from the distribution over X cross Y do we expect to be misclassified? So this is really what we care about, or some version of this, because we care about generalization. So how do we explain it? So I'm going to wave my hand a little bit here, just to give you some intuition. So really there are two components that are involved in understanding overfitting. One of them is called the variance of the learner. So basically, this is something that, again, is going to grow as a function of model complexity, and it measures how susceptible is the learner to minor changes in the training data. So think about the case where you have a huge complexity class, and you're changing the data set. If you're changing the data set, so the data set is sampled from the instance space. You have one sample as your training data, and you train a model. Then you take another sample as a training data, and you train the model. Because you have a very, very expressive class of functions, each training set is going to give rise to a different model, which means each training set is going to give rise to a different error of the model that you learned. Again, think about the two extreme cases. One case is you have one function in your hypothesis space. Doesn't matter whether you change the data or not. You're staying with this one function as your hypothesis. Or you have a lot of functions, so every change in the training set is going to give rise to another function. This is the variance. More accurately, we can actually talk about, for each training set D, you will learn a different hypothesis, H of D, and this hypothesis will have a different true error, E of H. And when I talk about variance, formally we're talking about the variance of this random variable. The true error as a function of the size of the complexity of the model. And hopefully intuitively you see that this is going to go up with the model complexity. Yes?
So this thing that it will give rise to a different error for each if we train on different data sets, this goes against our generalization thing, right? That we want the model to generalize well. So why would we want to increase the model complexity at any point?
Okay, good question. So that's a bad thing. You don't want too much variance. On the other hand, you want to think about bias also. So what is the bias? The bias measures how likely are we to identify the target hypothesis. So again, think about the two extreme cases. If you have one function in your hypothesis space, you look at the data, you're bound to choose this one function, the error could be large. If you have a lot of choices in your hypothesis space, every training set that you will see, you'll be able to fit it, and you'll be able to get as close as possible to minimum error of the hypothesis that you've chosen, right? So again, you can think about it in exactly the same sort of formal terms. For each training data D, you learn a different hypothesis, H of D. This hypothesis is going to have a true error, H of D, and we're looking here at the difference between the mean of this random variable and the true error. And again, it has to be clear that as your model complexity goes up, the bias is going to go down because you can actually fit the data. So on one hand, you want to be able to minimize this. On the other hand, you don't want to get too much variance. So the real picture is a mix of the bias and the variance. The expected error can be shown to be a sum or related to the sum of the bias and the variance. And again, the intuition is, on one hand, you want to have, you want to fit the data as much as you can. And for that, you need a lot of functions to choose from in your hypothesis space. On the other hand, if you have a lot of functions to choose from in your hypothesis space, your variance is going to be large, and that's a bad thing. So basically, what we want is we want to be able to figure out how to balance this bias and variance, or how to balance using simple models with complex models. And this is approximately the picture that we're going to see. So if we go with very simple models, we're going to underfit. We're going to have a lot of empirical error. If we go with very complex models, in general, we're going to overfit. We'll have very small empirical error, but who knows what's going to happen later on in the test data. And basically, we want to be able to find this balance. So I admit this is a little bit hand-wavingly. It can be made more accurately for specific loss functions. And later in the semester, we're going to discuss a somewhat more precise theory that allows us to trade the expressivity of models with the empirical error. And again, we'll see that sometimes we want to give up on minimizing the empirical error because we want to guarantee better generalization. So that's kind of the hint into the general theory. What are we doing in decision trees? We want to avoid overfitting. And basically, that means don't allow the tree to grow too much, because we already know that it can minimize the empirical error. And we want to do pruning. There are really two ways to do pruning. One of them is pre-pruning. That is, don't grow the tree too much. One of them is post-pruning. Learn the tree and then cut a little bit. And different packages that you'll use will allow you to do both. And there are various ways to guarantee that what you're doing makes sense, various statistical measures. The key one that we're going to use also to see how well we're doing is that of cross-validation that I'm going to get to a little bit later today. Basically, the idea is that as you train, you also reserve a holdout data set. We call it development set. And you measure the utility of learning more by the performance on this development set. So you don't train on it, but you measure progress on it. It's not the test data. It's just a set-aside fraction of the training set that you set aside in order to measure your progress. I already mentioned that this issue here, this game that we're playing here, is related to regularization, and we discussed last time, very briefly, how this can be avoided also in linear classifiers. We're going to talk about it at length next time. Okay, so how do we do pruning? There are really, as I said, two ways. One interesting way that I want to mention is that because you'll see it in packages, is that quite often the value of decision trees is that you can interpret it. And it's best if you can convert the decision trees into rules because they are more readable. And it's easy to do, right? So you can just go down the tree and make each one of them a rule, right? So if you have outlook equals sunny and humidity equal normal, say yes. Or outlook equal rain and wind equal strong, say no. So basically you went down the tree and you converted it to rules. The important thing to realize is that if you prune at the rules level, so you look at a rule, what does it mean to prune a rule, make a rule more generalized, general? So a rule is really a conjunction of things, right? Outlook equals sunny and humidity equal normal.
Remove one.
Remove one of the conjunct will make it more general, right? Why is pruning at the rule level different than pruning at the tree level? Yeah.
Does it have something to do with like what level you're? So if you prune, you could still prune. I guess this is a hard example, but you could prune something that's much higher up in the tree on one branch than if you were sort of uniformly cutting the lowest level.
Right. This is exactly the issue. So here the rules that I gave are only of size 2. So that's what makes this example hard for you. You can either prune the wind, or you can prune the outlook. But you can prune the outlook. Maybe your pruning rule, will decide that you want to get rid of outlook. This is something that you can do at the rule pruning level, but you will never do when you prune it at the tree, because you'll just start from the leaves and prune this way. So it's different. You just have to realize that it's different. Okay, so we talked a little bit about overfitting in the context of decision trees, just because it's the first and the easiest. I want to complete what we were talking about, our discussion of decision trees, with a couple of extensions. There are many, many extensions to the basic algorithm of decision trees. Two of them are more practical and important. One of them, in fact, was discussed at the end of last time, where there was a question about what do I do if I have real valued attributes? So in principle, we know we need decision rules at each node, right? We want to know whether the outlook is sunny or not. But for the same price, if we have a continuous variable, we can also ask whether the height is greater than 6,6 or not. So the question is only how to take continuous variables and make them discrete. And one way to do it is just to decide ahead of time, I'm going to come up with some thresholds and basically split it this way. Once we do this, we chose C, constant, and we look at the attribute value of A, and we condition on whether it's less than C or greater than C. Now we have a decision variable. Everything should go the same. Now, again, you can do it by deciding ahead of time that you don't really care about continuous variables. What you're going to do is you're going to do, if you have a continuous variable like height, you're going to do high, medium, short. That's it. Or you can split it and then find the highest gain. So you can take one simple way to do it, not the only one, is to actually do it in a data-dependent way. So you're going to take your examples. You sort the example according to the value of A. And then for each order pair XY, where the label is different between the example X and the example Y, the value X and the value Y, you're going to choose a value in the middle, say midpoint, because you have no more information than to choose a midpoint, and define two variables according to this way. So it's going to look something like this. Say you have a length attribute, and these are the values that you have for length in your data, 10, 15, 21, 28, 32, 40, 50. And underneath, I align the label, the class label. So for 10, it's a negative example. For 15 is a positive example. For 21 is also a positive example, and so on. So the breakpoints that I could choose are going to be between 10 and 15. I'm not going to choose any breakpoint between 15 and 21 because both are positive, and I'm assuming that everything in the middle is positive. I have no other information, and so on. So in this case, I'm going to have these 3 splits. Now I have defined new variables, new decision nodes for the decision tree, and I can keep on going. Now, this is not the only way. Maybe you have some other information based on other examples that you don't want to do it uniformly. You don't want to split in the middle between 20 and 15, but rather do something else. You could do it. But the principle is exactly the same. You actually reduce this continuous variable, continuous attribute to a discrete one and keep on going. Extension 2, missing value. So this is a very important problem, and we'll see it later on in the class in other more general contexts. But you can imagine that many times when you collect examples, say in the medical domain, you have a bunch of attributes that you care about. Say, you know that some diagnosis depends on fever, blood pressure, other blood tests. Some of these you have, some of them you don't. Perhaps because they're too expensive and you don't want to run all the tests. Perhaps because just people did not run all the tests. You still want to be able to learn a decision tree on this data, and you want to be able to evaluate the decision tree on this data. Right? So we have these 2 problems. First of all, training. I want to be able to evaluate the gain of the data set given an attribute A, where some of the examples are missing the value of A. What will I do? So here's an example. So we already decided that Outlook is our our root node. And now we're looking at Outlook equals Sunny, sort of the left side of this tree. Right? So we narrow down to a subset of the examples. Outlook equals Sunny. We have 5 examples. But in example number 8, we don't have the value of humidity. We still need to compute the information gain. So we started by looking at this set S sub Sunny relative to temperature. We computed the information gain. I'm going to repeat the computation of information gain just to refresh your memory and make sure that we are all together. So I put the formula for information gain up there. You remember that we start with the entropy of the set, and we subtract the weighted average of the entropy of S sub V. So in the case of when I'm looking at temperature, what do I have? I have 3 values for temperature. Okay, this isn't working today. 2 of them are hot, 2 of them are mild, 1 is cool. Everyone is looking with me on the temperature column here? Now, for hot, it's very easy because both examples are negative examples. So the entropy contribution of this is going to be 0. For cool, 1 example, it's positive. The entropy contribution here is also going to be 0. For mild, I have 2 examples. 1 is no, 1 is yes. So the entropy contribution here is going to be 1. So therefore, you look at the computation up there, it's 0.97. This is where I started with, minus 0, which is the contribution of hot and cool, minus 2/5, 2 of the examples, the mild examples, times 1. And that's the information gain of temperature relative to the set as Sunny. Okay? That's just repeating what we've done last time. Now I'm getting to humidity, and this is the interesting part. What do I do when I'm missing a value? How do I compute the information gain? Ideas? Yeah?
Create a new class. That's just unknown.
Okay, that's a good idea. So I can just say, you know what? I have other values. It's high, it's normal, and it's star for unknown. Maybe I will have some other stars in the data. And basically, I will treat this as a new variable. That's a good suggestion. I'm not implementing it here, but it's definitely something that can be done and is being done. I mean, you could also argue, well, you don't know that all the stars are the same. You know, it could be that some stars are due to this and some stars are due to that. If you don't have any additional information, we can just invent one star and go ahead. Other suggestions? Yeah?
You just ignore that data point.
Yeah, I can ignore this data point and basically say, I only have 4 data points for this, for the sake of this computation. That's another solution that I can use if I don't have a lot of them, or a large fraction of the examples do not have missing values. If I do want to use this,
count it in both the variables, like high and normal.
okay, so basically do something with it. So here I'm suggesting 2 ways. One of them is this. So one of them is choose the most likely value of xi. In this case, it's 50%. 2 are high, 2 are normal. I'm going to choose normal. And I'm computing in the top one relative to normal. So basically, that means that I have 3 examples that are split 0, negative. 3 examples that are split 0 and negative, and 3 are negatives. And 2 examples that are positive, 0, negative. So that's the way I do it. Another is to do fractional. So one important thing to realize here, no one said that this entropy computation has to be done with integers, right? Could be done with fractions. The same formula, plug in fractional numbers, it doesn't care. So in this case, for example, based on the ratio of the value of the other example, in this case it's half, too high, too normal, I can put half of this example into normal, half of this example into high, and what I'm going to get is that I have 2.5 examples with entropy, 0 positive example, 2.5 negatives, and 2.5 examples with 2 positive and a half negative. Right? Because I split this example to be half negative and half positive. This is going to be smaller than 0.97, and therefore I'm not going to choose this in this case. But basically, you can see that I have a range of possibilities here for how to compute information gain where I have a missing value. Other suggestions for doing it? Yes?
You could try to use some of the other information that you have from the x's. So in this case, maybe you would guess that since the temperature is mild and the only other mild instance has a humidity that's normal, you could guess that it's normal.
Excellent. So basically what you're saying, why don't I look at my data and try to infer what's a likely way to complete this missing value? And I can look at temperature, for example, as you said. What else can I look at here? Yeah?
You have the label as no, and all the other labels which have no have high humidity.
I can look at the label, right? You see that for the high, there is a no label that agrees with the label in my current target examples. For the others, I have no. Yes?
Isn't that just reinforcing what you were doing before without actually adding any data? It's like artificially reinforcing your previous conclusion.
What do you mean by artificially reinforcement?
What I mean is the classification that you came up with, excluding that data point, is just getting reinforced because you just forced this new data point to match it.
I'm not really reinforcing it. I'm trying to guess what is the most likely way to complete the missing value. And I'm assuming that there is some population here that is coherent in some way.
But if you can assume that that population is coherent by itself, then just get rid of the data point, right? Instead of assuming that it fits your other data.
Yeah, but if I'm getting rid of the data point, which is certainly a possibility, I'm losing other information, right? I do know that this has mild temperature, weak wind, and it's a negative example. So maybe I can use this information. But anyhow, this is a good discussion because sometimes maybe I want to get rid of it. Sometimes if I have a lot of examples that have missing value, what you suggested, and you suggested it in two different ways, by looking at different parts of the data, looking at the label, or looking at the other features, you suggested to kind of learn. It's a learning problem, right? You try to predict what could be the humidity of this example given the rest of the data. And once you can learn this, you can complete it and keep on learning. And this is going to be a very general procedure that we're going to actually put on more precise foundation later on. It's going to be called expectation maximization. We're going to assume that there is some model for the data. And if we are missing some values, we're going to try to estimate them using the other data that we have, plug it in, and keep on estimating. And we're going to see that under some assumptions, this model, this procedure actually converges to something that makes sense. So in the context of decision trees, everything looks discrete and not so kind of easy to justify, but it's really the same kind of procedure. You assume that the data was generated by some coherent model. There's some function behind this data. Something was missing, but you're going to try to estimate it weekly and then use it to reinforce and keep on learning. Yes?
So why the most likely value is normal? Not high?
First of all, I did not say that it's the most likely is normal. You're talking about the top suggestion. Why would it be high?
Because I mean, if the humidity is high, then it is not.
Okay, so let's separate. When I suggested the computation above here, this was before the discussion of let's try to learn from the data what is the most likely value. What I suggested there, let's just look at the humidity column and choose by majority. And I chose by majority. In fact, there was a tie between high and normal, so I randomly chose normal. That was the computation above. Later on, we suggested a few other solutions that are a little bit more involved. Look at other attributes, look at the label, and try to estimate based on these which is the most likely. And then perhaps I would agree with you that the selection of normal maybe is not the most likely one. Okay? But we don't really care. First of all, there was an evolution of the method. We talked about several methods here. This was the first one. And there is no clear solution. Say it again.
In the calculation below, it is high. Because
Which calculation says that it's high?
below,
The assigned fractional values one?
if you assign them, it will be normal, then the calculation is not.
I didn't get it. Say it again.
I mean, I think it's like it's 0.97 minus something. So this is assuming the mean value is high.
No, the second calculation assumes that it's fractional, that it's half normal and half high. Okay? Okay. Any other questions on this? Yes?
Will it increase the bias of the model?
Good question. What do you mean by that?
So we artificially choose what we want to fill in the community. So we add our personal preference.
Well, it's not our personal preference. We justify it by the data. But it does run the risk that it kind of pushes the model in one direction. And we have to be careful with that. So when we, as I said, when we talk about probabilistic models, we're going to make an assumption. We're going to make an assumption that there is some probability distribution that underlies the generation of the data. And the way we're going to learn the value of humidity in this case as a function of the rest of the data is going to basically try to fit this model. So, and we will show that this actually is the right thing to do. At this point, again, I'm still waving my hands a little bit. just saying that given this data, you can try to fill the gap or the missing value by trying to estimate what is the best or the most likely value. We didn't even define what does it mean to be the most likely. Other questions? Yeah.
At test time, if you have a missing value, what do you do?
Okay, so at test time, what do we do? Thanks. So now we want to classify an example without knowing the value of the attribute. So again, this is the tree. We already learned it. We're given an example here. And again, humidity is missing. So given this example, we're going to run down the tree. Outlook equals sunny. Humidity, we don't know what to do. How should we classify this example? Really, there are two options, right, for humidity. It could be normal or high, but each of them is giving us a different label. Not clear that there is something that we can do here.
We can look at the wind.
We can look at the wind. The wind is strong, which favors?
So we choose humidity to be high. Like the labels match.
To match the label. So that's certainly one option. But again, it's not clear if there is if this is justified for a single example. Another option that we have is basically to do some kind of averaging. So let's look at this example. In this case, Outlook is missing. I have everything else. What do I do here? One option, again, is to assume, you know what, Outlook has 3 values. They split about uniformly. So I'm going to basically split Outlook uniformly to these 3 options and just do it. So with probability of a third, I'm going to go left to sunny and keep on going down the tree. What will I get? Humidity is normal, so I'm going to get yes. With a probability of third, I'm going to go down to overcast. I'm going to get yes. With a probability of a third, I'm going to go down the rainy. Wind is strong, so I'm going to say no. So I have yes, yes, and no. I'm going to predict yes. So basically, I do it based on the distribution of the data. More correctly, perhaps I should have done it not completely uniformly because I have 5, 4, and 5 rather than 5, 5, and 5, but this wouldn't have changed anything in this case. Yes?
Would it be possible when you're building this tree to use this data point where it does have data? So, for example, use it in your calculation for outlook, use it in your calculations for wind where you do have data, and then only when you get to the node you have humidity, you actually don't have information, instead of trying to guess, just mix it there. Because
Okay.
you are extracting all the information.
I didn't have these examples when I learned the model. Right? So
Coming in at the end.
this is coming now as test examples. Right? I could, but probably you don't want to do this. So the standard protocol that we have in mind is that I train once, I have 10,000 examples. From now on, I'm going to fix this model and use it. I don't want to retrain every time for 2 reasons. First of all, not a good way to use my time or computational resources. 2, I'm going to overfit. Right? So you don't want to change your model whenever you see another test example. Right? So, and this is actually an important thing that we're going to talk about a lot later when we talk about methodology. Okay, so let me just briefly mention that there are many other issues that can come up in the context of decision trees, and in fact also in the context of other classifiers. So attributes can have different costs. At this point, I assume that all the attributes are equal the same. You know, if in the medical diagnosis example, you may think that some features, some attributes are more important than others. You can change the information gain to account for it. You may have other measures to selecting attributes, right? So we chose one that is based on the ID3 criteria, based on information gain. Could be others. For example, if you have multi-class classification, you probably want to change the information gain to account for that. in the problem set that I'm going to talk about in a few seconds, you will see we just suggested another way to measure attributes. Not going to be as good as the one we suggested in class, but it's not bad to play with them. There are many other ways to think about decision trees. So we think about decision trees as what I call axis parallel, right? So basically, we have, if you think about continuous variables, we always think about attribute less than C or greater than C. So if you think about it geometrically, you basically split the space into axis parallel regions. You don't have to do it this way. You can decide that if you have attributes A and B, the decision node is whether A plus B is greater than 5. What does that mean? That means taking a diagonal in the space, right? So these decision trees are called oblique decision trees, where the decisions are not axis parallel. Of course, you have to think about, okay, so how do I come with my decision nodes now? And there are algorithms that suggest to come up with better decision nodes and then learn a decision tree over these. There are ways to learn decision trees incrementally. So maybe the situation that you had in mind where data is coming in a streaming fashion and you want to learn a decision tree and make decisions as you go, kind of an online decision tree algorithm. Again, there are algorithms for this. Many things you can think about. Okay, to summarize. So one of the important things we've done is we presented the hypothesis class of decision trees. It's very different than a lot of the hypothesis spaces we're going to see in the rest of the semester. It's a very expressive function class. It's flexible. We presented the decision tree algorithm that is an important learning algorithm, and discussed as one of the important detours, overfitting and ways to address it in decision trees. Okay, so one of the things that I want to get to talking about is evaluation, because this is one of the things that you're going to start playing with in the context of the first homework. But before that, I want to talk about one other extension that is also important. We'll see more of it later, but you're going to meet it today when you see the first homework. So one way to use decision trees that turned out to be a very important way is, rather than using decision trees to represent one target function, use decision trees as features. So we talked already about expressivity of spaces, of functions, and we talked about transforming a function space to a more expressive one. And decision trees are being used in this way very productively. So if you just learn one decision tree, you can learn a very big decision tree. It's going to fit your training data very well, but it could lead to overfitting. Instead, you can use small decision trees. Each one of them by itself is not going to fit the data well. But together, if you learn some function over them, they're going to be a good classifier. So you can think about each one of them as an expert. It fits part of the data well. It doesn't do well on the rest of the data. And then the question is how to put these together. And there are multiple ways of putting them together. One of them that we're going to get to around the middle of the semester is called boosting, which is a very important learning algorithm. Also, it's a linear classifier on top of decision trees, but it's being learned in a slightly different way. In homework 1, you're going to learn a linear classifier over decision trees. And the linear classifier is going to be a rather simple linear classifier of the type that we talked about last week. So I want to talk a little bit about what you will do in homework 1, which will be out today. I don't know if it's already out or not, but will definitely be out today. Let's see if I can show you. Oh, you can see. Okay. So let's spend a few minutes talking about it. So it's out today, it's due in 2 weeks. As I said already a few times, I really think that you should start working on it today. Start asking questions. We're going to address it also in the recitations this week and next week. So there are 2 problems. One of them is a rather easy problem, just to make sure that you understand what decision trees are. I'm not going to talk about it. The second is a more typical homework that you will see the rest of this class. It's an experimental problem set. You will basically use data to learn multiple models. You will learn stochastic gradient descent model. We talked about it last time. You learn decision trees of different sizes. And you'll work also on feature extraction using decision trees. So again, most of the code is going to be given to you. You'll still have some work to do. I want to talk about one component of this, which is decision stumps as features, so that we can understand better what you have to do. Again, it's all is described there. You can try to read it now. Can you read this? Okay, so here is the idea. You have a data set. The data set has, I think, 500 features. You can learn a decision tree over 500 features, and this will be one of the things that you can do. But these features perhaps are not going to be expressive enough to really give you a good classifier. The idea that we're trying to explore here, or you are going to try to explore, is how to transform this 500-dimensional feature space to a more expressive feature space. So you can imagine taking some functions of the feature space. Again, if you think about the badges example that we talked about, and you will also play with here, basic features are going to be whether the first character is in the first word is A or B or C or 26 different characters. But you can also invent features that are, is the first character A, and the first character of the first name A, and the first character of the last name D. Right? Conjunction of these 2 features. These are more expressive features. They are similar to the example that I've given where you have points on the line that you cannot separate just with a straight line, but once you change the dimensionality and you represent each data point as x, x squared, suddenly you can do it. So this is basically the idea here. The question is how to generate these transformations, this function that add expressivity, and what we suggest to do here is we suggest to do it with decision trees. So you're going to take all your data, you're going to learn, let's say, 50 different decision trees, small decision trees on the data. By small, I mean you're going to limit the depth of them. So they are not going to be that expressive. They are unlikely to actually fit the data. So the first question you can ask yourself, what do you mean learn 50 different decision trees on the data? We have one deterministic algorithm. How can you learn 50 different decision trees? Suggestion?
You could randomize your first node. Only restrict your set to a subset of the x's when building each tree.
Okay, so actually you gave 2 suggestions. I'm going to build on your second suggestion. That's what we're going to do. We're not going to use all the features every time. So say you have 500 features. You're going to choose a subset of the features, let's say 50% of the features randomly, and learn a decision tree. Every time, you're going to choose a different subset. There's a huge number of subsets of size 250 of a set of 500 features. So you can get a lot of different decision trees. Let's say we choose to get just 50. So you do this 50 times. Each time you learn a decision tree. Now you have 50 decision trees that will learn on the data. Now you want to transform the data. So you take each example of size 500, and you evaluate the 50 decision trees on it. You get 50 predictions, right? Each decision tree says something else. So the first one says yes, the second one says no, the third one says also no, and so on. You get 50 values. Looking at these 50 values, you transform the 500-dimensional example into a 50-dimensional example that presumably is more expressive in the sense that it has a lot of information about this data point. Okay? You do this for all your data, training and test data. Now you have a new data set. You can learn anything you want on this new data set. What we're going to ask you to do is we're going to ask you to learn a linear stochastic gradient descent algorithm on this. So essentially, what you're doing now is you have a stochastic gradient descent linear algorithm on top of 50 decision trees. That's going to be the most challenging part of this data set. Questions? Yeah.
In the notion of like the random forest where you don't build a linear model on top of those 50 trees, instead you just use those 50 trees, you have an averaging operation at the bottom to generate your prediction. How is that different from the
So we don't know what random forest is. Random forest is basically a similar idea where instead of learning a model on top of the decision trees, you just average them. Learning a linear function is more expressive than averaging, right? Averaging is a linear model with equal weights. We're going to get to talk about, or mention at least, random forest when we talk about boosting, because it's a little bit related to this. So it's not the only way. What we are doing here is not the only way to combine decision trees. Random forest is another one. Bagging is another one. Boosting is another one. We're going to mention these a little bit later in the semester. In all these, specifically random forest, rather than learning 50 decision trees, people would learn 50,000 decision trees, a huge number. And there's some statistical justification for why this makes sense. I don't want you to learn 50,000 decision trees here. 50 is going to be good enough to make a point. But on the other hand, we're going to be a little bit more expressive by learning a good linear classifier on top of this. So hopefully it will be simple enough to run, not too time consuming, and still we learn something. Yeah.
Do we have the flexibility of experimenting with ways of making 50 decision trees?
Okay, so in all these data sets, in all these problem sets, you can do many more things than what we suggest. In one case here, you will see we give an extra credit for doing something beyond what we asked. You can do many things beyond what we asked. What we say here is the minimum. You can definitely experiment with other ways of doing it. And you will see that it's quite easy, because if you're organized in what you're doing, it's going to be very easy to run other experiments. And this is one of the lessons that I'm going to repeat on during the class, and in fact, even today. You're going to run a lot of experiments. Be organized. I mean, don't force yourself to sit next to it and observe everything that is happening. Write scripts so that you can make sure what is being done, record everything that is being done. You can go to sleep and let your problem set be completed while you're asleep if you're organized. So, and then you can add stuff in an easy way. Question on this? I know that this is the part where people often struggle conceptually, so we try to add a high-level description. I spent a few minutes now. Hopefully this will be clear. Okay, the rest of this problem set requires you, so you're going to experiment with this. You're going to do a few things that are important from the experimental methodology perspective. And once you're done with all this, you're going to run the same thing also on the badges data set that you saw before. The difference is that here we are actually giving you the examples. We extracted features, we just give you Boolean features. In the badges game, it's a little bit more interesting because we just give you data. You need to do the feature extraction yourself, which is a more realistic scenario. We give you one set of features that we want you to extract. You're going to have examples of 260 dimensions. You can do more. So as extra credit, we ask you to try to extract other features, see how good a set of features you can extract and how good the predictors that you get will be. Questions? Okay, so hopefully this will be fun, and you will learn something from it. I think you should. Okay, so let's continue here. Okay, so we talked about decision tree as features. We talked about all these issues. Okay, so one of the things that you're going to be exposed to first time with this homework is machine learning is really an experimental field. And most of the problem sets are going to have a significant component of running experiments and trying to understand the results of the experiment. So I want to talk a little bit about how we do this. So there are some basics. I mean, well, I already talked about be organized and write scripts. The basic is that you split your data into 3 sets. You have training data, you have test data, and you have development data. Now, in real life, you sometimes don't have test data because eventually you're going to learn a model and launch it somewhere, and the data is going to come. You don't have any control on that. But you will still take the data that you do have and do that with it, so that you make sure that the model that you learn actually is going to behave well, or at least you'll have an estimate of how well your model will behave when you put it out there. So the idea of the development set is that most learning algorithms will have some parameters, and you'll have to tune them. You don't want to look at your test data, because if you do look at your test data, you're basically going to overfit this test data, and any number of any performance that you then report on it is meaningless. I'm not saying that people are not doing it. When you read papers, they do, but you will not, at least if we want to get some understanding of how good we're going to be. The development data is set aside exactly to allow you to do this. Okay, so once we have this, how do we measure performance? So we train on the training data, we test on test data, we have this development set. We want to have some metrics. So the basic metrics that we deal with is that of accuracy. We talked about before. What is accuracy? Basically, number of correct predictions divided by the number of test instances. Okay, that's the simplest thing that you can think of. If you have a binary classifier, this makes sense. Sometimes. When would that not make sense? You see any problem with measuring your performance using accuracy? Yeah?
If one of the classes is too frequent, so if you have like 1,000 training examples and 900 of them are yes, then this is not exactly representative of how well you're doing.
Right. Any other suggestion different than that? Yeah? Cost could be also important, right? So you'd never want to make mistakes on positive examples. But it's okay to make mistakes on negative examples. That would also be a reason. Both of these, I'm going to offer one solution that is important here. I want to focus first on the first one because it's really very important and very frequent. In most interesting problems, most of the data that you have actually is negative examples. And very few of them are positive, and you care about this. So what will happen if you measure the data using accuracy? If you have 99% or 95% of the data negative examples, you can just say no. And your accuracy is very high, 95%. You're happy, but it's completely meaningless, right? Because you really care about your performance on the positive examples. And that's why also the issue of cost is relevant here. You care about your performance on positive examples, so just saying no isn't a solution. So this is even more important when we talk about multi-class classifications. If you have 10 different labels, it's rare that you see that they're uniform, and you want to be able to measure your performance for each class label separately. So what we do instead is we use something that is called recall and precision. So recall is going to be, I'm talking again about the scenario of binary classifiers. It's easier this way. It's in the denominator, I'm going to have the number of all positive examples. And then I'm asking myself, how many of the positive did you get? That's recall. The number of positive identified out of all the positives. The precision, again, is I'm looking at the number of positive identified out of those that are predicted positive. So I predicted on some population positive. I want to know how precise am I. So what fraction of these that I predicted positive are really positive? Let's look at it in this picture here. So what do you see here? On the left side, the darker green are my positive examples. On the right side, my negative examples. Okay? Now, what you see in the circle are my predictions. So the left side of the circle are those that I predicted correctly. There's the true positives. On the right side, these are the false positives. So, and what you can see here in the bottom right is graphically the same definition that I had there, right? So what is recall? Recall is on the right side. How many of the positive examples did I get? Okay, so I have in the denominator all the left side, the green, dark green, and in the numerator I have those that I predicted positive. And precision, what I have is all the circle in the denominator. These are the examples that I actually predicted to be positive. How many of them are really positive? This is telling me how precise I am. So basically, let's take an example here. Let's assume that I have 100 examples. 5 of them are positive. If I just say no, I'm going to get accuracy of 95%. Of course, recall and precision are going to be 0 here. On the other hand, let's imagine that I said 4 are positive examples, and out of these 4, 2 are indeed positive. In this case, my recall is going to be 2 out of 5, right? I got 2 out of the true positives, the 5 true positives. My precision is 2 out of 4. I predicted that 4 are positive, 2 of them are correct. So what I have here is 40% plus 50%, or 40% and 50%, which is probably better than 0 and 0 recall and precision. Another way to look at this is to look at the confusion matrix. In the confusion matrix, I'm going to put it's going to be a matrix of actual class labels and predicted class labels. So in this case, I have a binary classifier, yes, no, on the vertical side, yes, no on the predicted horizontal side, and the true positive and the true negative are in the diagonal. I hope that these numbers in the diagonal are large numbers, and I hope that the false negative and false positive are small numbers. So if you think about accuracy, with this notation here, accuracy is the denominator is positive plus negative, everything. And in the numerator, I have the true positive plus the true negative, the diagonal. On the other hand, if I think about precision and recall, what I have in precision, I have in the numerator true positive plus false positive, those that I predicted positive, and then I'm looking at what fraction of them is indeed correct, true positive over this. And recall, I have true positive plus false negative in the numerator, and I'm asking how many of these positive I got, true positive divided by that. So this is the same thing, just looking at it in slightly different ways. And I want to mention that this notion of confusion matrix is actually quite important in general, not only for the binary case. If you have multi-class classifier of, I don't know, 10 labels, you also may want to draw the same matrix. It's going to be 10 by 10 now. And the ij cell is going to indicate how many of the I labeled examples will predict a j. And this will give you a good idea of how your predictor is behaving. It will also tell you what kind of mistake you're making. Because maybe you'll see, you know what, on the I label, on the fifth label, I typically think that it's number 6 and number 7. I don't think that it's something else. Maybe it gives you some hint about relations between class labels and so on. So this is always a useful thing to do. Okay, so basically, hopefully I convinced you that it's important to look at recall and precision. Moreover, it's actually makes sense to look at them together. Not only recall separately and precision, but rather look at the curve. So without the details of this curve that I show here, what's important to you to realize is that there's a trade-off between precision and recall. All right? So if you allow yourself to have very low recall, the chances that you'll have higher precision are high. On the other hand, as your recall grows, your precision is going to go down. And you may want to care about some kind of a balance between these two. So there are several metrics that account for this curve. You can think about the area under the curve and various other things. I'm not going to deal with that. I'm going to just deal with one way to combine recall and precision, and it's called the F measure. It's combining recall and precision by looking at the harmonic mean, which is parameterized by beta here. So what you see here is 1 plus beta square times precision times recall divided by beta square times precision plus recall. F1 is the one that is most commonly used, so plug in beta equal 1, and you'll get what you'll see a lot in the literature of F1. It's not the only thing that is being used. It's really a function of whether you care about emphasizing recall over precision or vice versa. Okay, so before I move on, I want to say one thing that I forgot to say, and it's important to us because really what we care about is comparing classifiers, and we're going to talk about the beginning of next time, how to do it, and what are kind of what is the right methodology to do it. I want to mention one thing. So we talked a lot about training data, test data, and so on. You will see that in the homework, we ask you not only for your performance on the test data, but also for your performance on the training data. And that's an important thing for you to do from now on throughout your life. Always look also at how you do on the training data. Why do I think this is important? Yes?
If you're not performing well on the training data, then
could be an accident, or you started by saying if you don't do well on the training data, something might be wrong. Maybe you're not using the right hypothesis, maybe you're not expressive enough. That's one aspect. Another aspect, yes?
If you're doing too well on training data, you could be overfitting.
Exactly. So you want to know these extremes. What's the relation between how well you do in the training and how well you do in the test? If you do very well on the training and not so good on the test data or the development, then it means that you're overfitting, you want to do something. So you really, it will increase your understanding of what's happening here and whether your prior decisions were correct in terms of choosing the hypothesis class correctly, choosing the learning algorithms correctly, using the right features. This will add something to your understanding of what's happening. So you will see that in the homework, we ask you to look at how well you're doing on training before you look at how well you're doing with a procedure that we're going to call five-fold cross-validation that I'm going to introduce next time, introduced also in the data set. Final questions? Yeah.
Can you go over what the development data is again?
So the development data is you sample your training set and you put aside 10% of the data so that you'll be able to measure your progress. Test data is something you never look at, but you still want to know how well you're doing. Whether you overfeed the data, whether you underfeed the data, maybe some of your algorithms require some parameter tuning. You're going to do this by observing the performance on the development set. Other questions? Okay, see you Wednesday then.
What do you mean by expressivity of the model? You said that digital trees are more expressive, so what do you mean by expressive?
So why didn't you ask this in class?
I was actually asked to pronounce it and
No, but you should ask me because that's a question that many people care about.
I googled also, but I can't find anything.
So what I mean is, roughly speaking, how many different members are there in the hypothesis space?
Many different members.
Yes, how many functions can you learn? If you learn decision trees, all Boolean functions can be expressed in the decision tree. So it's a very expressive class. If on the other hand you learn only decision trees of size 8, of depth 8, not all functions can be expressed this way. Not all Boolean functions can be expressed as decision trees of size 8. And that's what I mean by expressivity.
I'll do some thinking over it and I'll get back to you.
Okay?
Thank you.
I did email you like last week about this, Professor Wall. So you just need to sign here, I think, and then you might need to indicate here, or I can figure it out.
So what do you want to do?
Just swap from 419 to 519.
Okay, that's a red pen. Do you have another pen?
Color black.
That's better. Okay, I think it's everything here, right?
The email, I can also fill out the email as well, but yeah.
Yes, you can.
All right, thank you.
Yeah, the exact same things.
Thank you. Okay.
Is that all you need? Yeah. Well, I'm just gonna go up to the guy, the top tier. You can
So
go.
you're moving from.
419 to 519.
Same situation.
Okay.
Yes.
Okay.
Thank
All right,
you.
thank you so much.
Sure.
Professor.
Are you going now?
Oh, same course. Okay. So you were on the waiting list,
Yes.
and you are, what department are you at?
I'm at the college, College of Arts and Sciences.
Oh, I see. That's why you couldn't be added automatically?
Right. So I have to hand in this submission, this petition to the college office, and then they will consider it.
I see. So where do I sign?
You can sign here.
It's a pencil or?
It's a pencil, mechanical pencil.
Not good.
Oh.
I have to sign with real pen, so it's red, but hopefully it's going to do the work.
Oh, great.
Okay.
Thank you so much.
Any other signature?
No, I just had a doubt.
Okay.
Professor, you had discussed variance and bias in the class. I didn't understand the difference in them. Like, I understand that for different sets of data, you get different classifiers, and each of these classifiers would make errors. So, is the variance of those errors?
Yeah. So it's read the slide carefully. It's completely defined there.
Okay.
It's the variance of this random variable, which is the true error once you change the data set.
Okay.
So you sample a training set, you learn a model, you get a true error. You sample another one, you get another model, another true error. So think about the true error as a random variable. The variance is the variance of this true error, of this variable.
Oh, okay.
And bias is the difference between the true error that you get for this variable and the true error of the function.
Oh,
And this is going to go to 0 if you have a very expressive class.
so if we use the entire data, then variance is 0. Sorry, bias is 0.
No. The bias is not defined on. The bias is a bias of a random variable. So you need something random here. So the random here is the data set that you choose. For different data sets that you choose, the different training sets that you choose, you get different values for the true error of the model. Right? So here is the protocol. This is the instance space. Let's assume that you choose half of it as your training set. Okay? You can do this 1,000,000 times. Every time you get a different model, each model has its own error, true error, on the real data. You measure the variance of this variable, and that's the variance that I defined.
So bias would be in that sense.
And bias is exactly the same thing. You do the same experiment as they describe, right? So you sample, say, half the data, you learn a model. Someone told you the true error that you can have in this data, on this data, and you measure the difference between the real true error and what the model gave you.
Just for that subset of data.
For that, but you do it many, many times, right? So this is where the random variable comes in.
Oh, okay.
It's a theoretical construct, right? But the process that you can imagine is this, that the values of the random variables are given by looking at the true error on different samples of the training data.
So in that case, bias would have many values, because the true value.
No.
Minus
Bias is really the difference between the average that you get over everything and the true error.
Oh, the average and the true.
Yes,
Okay,
yes.
Professor, and just one more. You spoke about pruning at the tree level and the rule level.
Yeah.
So the difference is in the tree level, you cut out an entire branch or something like that?
In the tree level, you go from below.
Okay.
You start cutting trees.
You go from below.
Sorry, leaves.
Leaves, okay.
Yeah. And in a rule, I give you a bunch of rules. You can do whatever you want, right? So typically, generalizing a rule means eliminating one of the variables.
Basically, you're cutting down a tree, entire.
No, not necessarily, right? So I'm looking at it as rules.
Okay.
the impact on the tree could be very weird, right? Because if I cut a node that is at the top of the tree, but I didn't cut something below it, which is possible, I don't know what it means. No, it makes sense, right? I can evaluate it, but I cannot draw the tree again. Right? It's going to be a tree with a hole.
Okay. Nice.
Yeah. So that's why I just wanted to point out that it's different. If you go to C4.5, C5.0, the packages, you will see that you get options of how to prune. And you just have to understand that these options are really different.
Thank you, sir.
In boosting, do we make parts of a training set and then different decision trees are trained on different subparts of the same training set, or all the trees are trained on the complete training set?
We didn't get to boosting. We'll talk about boosting in a few weeks. I just mentioned it. Boosting is a slightly more sophisticated algorithm where you basically, based on your performance on the first tree, let's say, on the first, it's going to be called weak classifier, you choose the next classifier. So it's an incremental algorithm.
Okay.
While here, the way I described it, I first learn all the 50 trees independently.
On the same, on the complete data set?
Yes, that's the way I described it here.
Yeah. So like what will be the difference? I mean, the same algorithm, same training set, then?
Okay, it's a good question. When we get to boosting, you'll be able to see the difference. So the key difference is that, well, two differences. One is how you choose the decision trees. So let's imagine that the bottom we have decision trees, and on top of it we have a linear classifier. The way I described it and what you will do in the homework, you choose random decision trees for the bottom layer, and you learn a linear classifier. So you assign weights to these features by learning one linear classifier on top of them. In boosting, on the other hand, you learn the decision trees incrementally. They are not independent. So the second decision tree that you learn is a function of what you've learned in the first. And the weights are also a function of that. So the weights you assign to each tree are not learned together like you will do here, but rather they are learned incrementally. So, and there's a theory that shows that doing boosting is the right thing to do. So this can be shown under some assumption to actually converge and do the right thing. For all the other algorithms, people mention random forest, bagging, and so on, there's very weak proofs of why they are working. They are working, but the theory is not completely well defined. Okay, sure. Hi.
I would like to ask this, when we calculate the most likely value.
By the way, I changed the slide, so okay, this is the earlier version.
So, I mean, in this, we can see that there are two high and two normal.
Yeah.
And this is under the condition of outlook equals to sunny.
Yes.
Under this condition, normal is 2 and high is 2.
Yeah, that's why I changed it, so you will see just the relevant examples.
So why shouldn't we look at the whole data set and look at the community in this line?
I'm not saying you shouldn't.
It's another way.
Yeah. So we had a long discussion of various things you can do.
Okay.
Definitely you can do this. So I will change this to mean majority, because this was one of the options.
Yeah.
But we talked about other suggestions. Yeah.
And this is what I'm doing this weekend about to train a classifier on sub-events, the relation of sub-event and the super event.
Okay, so let's not do it now. We're going to have a meeting tomorrow.
Yeah. I'm just asking that, class 1 is represented as the relation exists, and class 0 represents the relation doesn't exist. And now my model presents such a position is One-
99.
Yeah, but class 1 is really low, only 14. And recall, the class 1 has 85.
What's the baseline? How many are class 0 and how many are class 1 in the data?
What do you know? I don't know.
So class 1 is no relations, class...
Class 1 is A and B exists a relation, and class 0 is A and B doesn't exist.
How many of them doesn't exist and how many of them it exists? In the data?
A and B without the relation consists of about 95%.
Okay, that's
Yeah.
fine. You get 99%.
Yeah.
It's a much easier problem.
Yeah. Yeah. So this model is not good enough, I think.
Yeah.
So
which data are you using?
what,
Which data is this?
HIEBE. HIEBE.
Oh, so that's the one the Muhal gave you?
Yeah. I'm just asking, so this is not good enough. So what is a good
Which model are you using?